Good morning. Are we all doing well? Good stuff. Okay, the presentation I'm going to give you today is about a job. Let me just fast forward this on. Here we go. About a job that was completed in 2021 to Lough Atalia Railway Bridge there in Galway. And I hope you find it interesting. Now, like a lot of things, we were slightly delayed through COVID finishing, but we got through the other side. All right, so just a bit about Irish Rail as a way of introduction. About the national network. This is the Republic of Ireland. So the company is semi-state company Irish Rail, which in the Gaelic language is Airond Éireann. They own, operate, maintain the network over 2,400 kilometres of track with a team of over 4,100 colleagues. Now, within the Chief Civil Engineers Department, the track and structures are managed in 3 divisional areas. That's of Athlone, Dublin and Limerick Junction. So my position, the Senior Track and Structures Engineer, which is the lead engineer, the route's in blue. I thought I'd just start with defining what I mean by sustainability. So what is sustainability? It's recognition that there are limits to the Earth's natural resources and its ability to withstand ever-increasing human impact. Sustainability is meeting the needs of the present generation without compromising those of future generations, or meeting human needs within ecological constraints. But beware, this is a word that's overused and often abused. Now, building a sustainable future is a profoundly complex problem. And while there's no oven-ready solutions to these problems, there are better or worse approaches and decisions. And the bridge I'll talk to you about is an example of a better design choice. Concerning sustainability, I must mention Irish Rail has a corporate strategy for sustainability, which you find online at that address, and the document sets out the sustainability goals and commitments and actions across the business. The goals align with and support the United Nations Sustainable Development Goals, SDGs, and Ireland's Climate Action Plan and the National Development Plan 2021 to 2030, amongst some other strategies. Okay, and in the foreword to the document, the Irish Rail CEO, Jim Mead, he sums up the strategy as from platform to boardroom, sustainability is a journey to which we are committed. On decarbonisation, we have a plan. It's our Climate Action Plan. And within infrastructure, we are changing our approach to more sustainable procurement procedures. We need to change to consider the whole life cost, not just upfront material costs. And this includes understanding and assessing whole life carbon, not just the initial carbon. We're committed to integrating carbon calculations into the business, starting with major infrastructure projects. We've chosen prioritised projects because industry figures, they suggest that where the biggest impact on carbon reductions can be made. In the projects, typically 70 to 80% of embodied carbon is in new materials, and 25-35% is associated with the installation of those new materials. So once installed, there's little opportunity to reduce carbon during an asset's life. We're committed to reduction in emissions and have initiatives ongoing across the business to seek reductions in carbon emissions. For example, a current rail supplier in carbon emissions is investing in decarbonation technologies which will reduce our carbon emissions by 50% from 2025. We have a feasibility study looking at reducing engine emissions on older OTM, on-track machines, and we're adopting low emissions mobile plant, small power tools, and purchase battery-operated equipment. We're also committed to adopting circular economy principles. We're examining options there for reuse, redundant ballast, and sleepers. Now, when we consider our options for intervention to an asset such as a bridge, in the real world of an operational railway, we have many factors to consider. Here I've highlighted 4, which are affordability, operational need, track access impacts, and the priorities. So in a railway environment where the constraints on time and access are premium, it is tempting to prioritise the shorter gains of installation time, construction system, initial cost. And the above challenges typically manifest in the offsetting of the renewal option. It's therefore even more critical that we understand the residual life of both the individual components and overall track and structure system. And with knowledge of residual life, we can choose appropriate maintenance interventions. In other words, if the renewal is not affordable, we can still utilise our asset knowledge to ensure the maintenance strategy is optimal. So in summary, there's many factors that come into play in making a decision on the intervention option. Now, after that brief introduction, I'm going to tell you about the project at Lough Atalia Bridge in Galway City. And the project involves structural repair and upgrade of a heritage double-track bridge. Here we see an aerial photo of the bridge across Lough Atalia, which is a sea lock. And trains arriving into Galway, they sweep around a right-hand curve from the top right with a wonderful vista of the lock and arrive into Kent Station, Terminal Station, the bottom left. Now, until I started putting together this paper, I hadn't realised the history of the bridge and that it was groundbreaking in its time. And I have a slide coming up on that later on. Now, the eagle-eyed of you might have already questioned how come I can only see 4 spans, three piers. And I have a slide that explains that now. The reason being, originally the bridge rotated around an opening span on the central pier. And from a structural point of view, we regard that 3rd span as being fully supported above the central pier. So hence the 5 spans. So this is what the bridge did originally. And the reason for the opening spans was the Admiralty, as conservatives of the navigation, insisted on the bridge being movable, so as to give 60 feet clearance, conceiving that at some future date the lock might be converted into a harbour or floating basin. It never was. Reputedly, the bridge was opened just once, on the first day of railway operation, 6th of August 1851. So in our asset management, in our infrastructure asset management system, which we abbreviate to IAMS, we break the bridge down into into sub-assets, and here you see the 5 spans labelled. The convention is we always go from the low mileage end to the Dublin end, from the right-hand end is span 1. The original swivel span of the bridge is recorded as being groundbreaking in its time, in that it was the longest swivel span in the world when constructed in 1851. Design was patented box girder supplied by Sir William Fairbairn from his foundry in Manchester. And Fairbairn's famous for developing the box girder for the Britannia Bridge, which spanned the Menai Straits on the rail line from Anglesey, North Wales, which opened in 1850, so just a year before the Galway opening. Onto our upgrade works. In 2011, we started a programme of structural repairs of the piers of the bridge, and here the photos illustrate split and cracked pier masonry just below the bearings. The masonry blocks you can see are visibly out of line with the face of the pier. The diagnosis was we had problems with the bearings, in that they were no longer working to allow longitudinal movement. Here again, the symptoms of the bearing problem can be seen on the central pier, cracks running down 8 courses of stonework below the bearing. Now, Lough Atalia Bridge has already experienced a long life, despite increasing demands being placed on it. With careful stewardship, correct interventions, the bridge can remain in service for many years in the future. And this, as we know, is a more sustainable approach to prioritise refurbishment over new builds. In the slide here, our structural department designed a remediation by way of stitching, tie bar enhancement to the areas below the bearings of the piers. The photo on the left indicates the placement of the stitching bars, and the sketch on the right is the tie bar anchors. And these tie bars pass right through the pier, anchored on the same fashion on the far side of the pier. So here's the completed pier works. It's noticeable, but it's a tidy repair. We then addressed the failed bearings, and here are photos before and after replacement. We replaced 6 bearings in a 50-hour possession by jacking up the beams and replacing bearing plates. And this was done in 2012. Through 2012 and into 2013, our bridge gang went meticulously through the bridge from one end to the other, carrying out extensive repairs. And here's just a sample of the many photos illustrating rivet replacement, plating works, stiffener repairs prior to painting. The plan at the time was to complete steel repairs 2013 and then finish the bridge with track renewal. This didn't happen. The track renewal was deferred in 2013 because the extent of the steel repairs and the rivet replacement was required. It exceeded the budget that had been estimated, and the budget assigned to the track renewal was diverted to finish the steel repairs. The lesson here is you really don't know how bad something is until you've had a thorough look. Much of the bridge was difficult to access, so we estimated. And when we shot blasted and it was done to clean down the metal surface in advance of the repairs, it threw up a lot more work than we'd anticipated. Now in 2013, had the track renewal gone ahead, it would have been an embedded rail system like this. We'd have eliminated the timber way-beam for embedded rail. And we've used this system widely on bridges across Irish rail network, and it's considered a standard replacement for timber way-beam bridges, the nickname silent bridges. The deferral gave us an opportunity, though, to reconsider the track design. Although it was approved and already designed, Lough Atalia, design at the bottom of the slide, the embedded rail system would require extensive and costly conversion of the structure to carry the steel rail holder. And whilst we might have come to consider these embedded rails as a standard solution, there's nothing standard about our heritage bridges. And I should add that it's no reflection on the embedded rail system. It's a good system, in our experience, absolutely. Once it's in place, it's just Lough Atalia needed major alteration works to accommodate the embedded rail. So the existing timber way-beam system had significant design deficiencies. Here I've highlighted the notched way-beam arrangement sitting on transverse timbers which support the walkway. And the arrangement existed in spans 1 to 4. And note the way-beam doesn't have great depth. This is due to the constraint of the station in close proximity, dictating the rail levels for the platform heights. Top right is an image from underneath, shows a decayed transverse timber. This is the situation of concern to maintenance staff, causing track twists, illustrates how the deterioration could be hidden if you're on the walkway above. And the sketch where I have illustrated on bottom right how a decayed transverse timber can cause twist on the rail and the way-beam deflects. In span 5, the way-beam was supported differently with transverse beams, and that was a legacy of where a turnout used to be situated on the span. So in any track design, this different support arrangement had to be taken into consideration. So in 2013, when the track replacement was deferred, we conducted a thorough inspection condition assessment of the timber track system. Here's an example of the condition rating traffic light report produced for the transverse timbers. And the red needs replacement, amber's fair, and green is good. The purpose of the condition rate in 2013 was to identify necessary works to keep the track going for around 5 years while we reorganised the track upgrade. And just a note here about the label in the box, which is a simple referencing system we devised. So the DU, that's down track, U is up rail, slash, the next number is the first span, number 1, and then the bay within the span, so third bay within the span 1, and then finally the number of the transverse timber. So we had this referencing system so that all our work could be managed through work orders on our IM system. And all the red and amber timbers were assigned work orders to be replaced in order to keep the track going. And managing at this level through IMs provided great visibility, and tracking of work gave us the assurance about the condition. And this is the first time we'd used IMs to drill down to this level of detail in a track system. Proved a great tool, really effective for giving visibility. Prior to having that referencing system, we didn't have greater detail than just a span level, so that, for example, we could see some replacement had been done in a span, so 2 timbers on the down road somewhere in span 1, but no real detail what and where within the span. So reflecting now on the deferral of the track upgrade, it was an opportunity to rethink the design. It was an opportunity to update my own views and those around me about our standard design approach and towards alternative, more sustainable track design solution. If you recall back to the earlier slide with the puzzle pieces about intervention options, the track access impacts are high for conversion to embedded rail. We were looking at shutting down each track for an estimated 338 days of work. Now, some works could run simultaneously, so we'd shorten this a bit, but even a reduction of 20%, 30%, it's not going to change it being high impact. On affordability, the embedded rail option is a high initial cost, both monetarily and in embodied carbon. Now, it's hard getting data on CO2 equivalent values for many track materials, but you can find global averages for steel to give an approximation fairly easily. And we knew the quantity of steel for the rail holders was 118 tonnes, so we could assess the CO2 equivalent for those which was in excess of 212 tonnes CO2e. And CO2e, the CO2 equivalent, if you're not familiar, is the way of bundling together all the greenhouse gases and expressing them as a single number. So the challenge in rethinking the track design was, could we do better? Now, when thinking about the track design, here's an image that caught my eye. We gave it some consideration discussion. It's March 2018 in a trade magazine. It shows a full depth timber webbing, no notches. And note the red arrow pointing to the base plate for check rail or guardrail. Now, in our upgrade, we wanted to provide some enhancement in terms of protection from derailment if we could. The bridge girders prevented a guard outside the rails, so check rail was in our thoughts as a betterment that would help prevent derailment occurring on the bridge. And whilst the arrangement shown had some benefits over the existing arrangement, the drawback was it would require a lot of additional works to achieve the silver clamping down arrangement that would prevent overturning of the webbing. So again, could we do better? We then started thinking about composite materials, and in particular, the FFU synthetic timber material. We'd used this for the first time in 2017 to replace like-for-like timber webbings on a 5-span bridge in Limerick of 135-metre length. Here's some bullet points on the benefits of composite materials, which include increased asset life, improved sustainability, and reduced whole life cost. With our first FFU installation, we certainly found that it required very little maintenance. There had been no screws coming loose, which was a problem in the previous timber webbings. So what might be possible with composites, in particular FFU? A good place to start was the manufacturer's website to get inspiration about what you could do with the material. Here's a bridge from the Netherlands where you can see FFUs used as transverse sleepers, shows some detail on fixing down arrangement, which was of interest. Here again is another example, FFU transverse sleepers on a bascule bridge in Belgium. Fixing down arrangement is shown again. This all helped stimulate and develop ideas about how FFU might be a good option. So cutting to the chase, by mid-2019, we decided on the new design seen in the extract here. It uses FFU transverse sleepers in spans 1 to 4 instead of a longitudinal webbing. The benefit with this is the FFU sleepers can carry a grating on top for the walkway, which eliminates the notched arrangement of the timber system, which was a very poor design detail. And in span 5, we came up with an FFU longitudinal webbing design because of the different support arrangements. So you'll see some images in the next slides. In terms of sustainability, primary benefits, choice of FFU are the long service life, low maintenance, less corrosion to the bridge by elimination of timber to steel interfaces, and the use of FFU material enabled us to do things to improve the design we couldn't do in timber, such as extending the sleepers to carry the walkway mesh. The installation work was all done at night in non-disruptive possessions, and the track returned for normal running of trains in the daytime. This is good for our customers, not having shutdowns. This sequence of pictures from left to right show the lifting of the timber track system. First the rails and the webbings removed in the left, then in the middle transverse timbers are removed, and on the right we see the exposed rail bearer and girders of the structure. The FFU was installed sequentially in panels starting one end of the bridge. In the left-hand picture, an FFU track panel ready to lift in, and you see the angles for the fixing down arrangement. Also note how the sleepers are extended in length to support the walkway grating. In the top right-hand picture, you see staff making up an FFU panel. The dust mask being worn at an industrial vacuum machine used because of the glass fibre dust from drilling the FFU. And now, it's not a big health and safety issue, but the dust can be an irritant. If it gets on your skin, you rub it or you inhale it. So, and in the bottom right, you can see the rail base plate. It's 3-heg type. We fitted a UIC 54 running rail with a UIC 33 check rail. Standard one for us now. It's the same base plate used throughout the bridge, and underneath there's a resilient pad to damp vibrations and a couple of 5mm FFU shims. Now we shimmed up during the installation so that we can make adjustments at the end by removing shims to achieve the final rail levels. Here in the left-hand picture is the FFU track panel being lifted in. The right-hand picture shows the fixing down angles and the bolted connections. And here progress is evident. The left-hand picture shows the downside track upgraded with FFU, whilst the upside is still timber webbing. And the picture on the right, it was showing the extended FFU sleepers carrying the walkway grating. Now these are cantilevered, they're not touching the structure, and in the left of that picture, you can see some rust patches where the old timber used to bear, which was the issue of this interface between the timber and the steel structure. And the benefit there is it keeps the air circulating, eliminates possible moisture traps on the bridge structure. For span 5, we created an FFU longitudinal way beam of 700 millimeter width by bolting together two 350 mil FFU pieces. And the same 3-hag base plates were used on this way beam as on the sleepers. So the base plate was 580 millimeter base plate to accommodate that in the 700 millimeter width way beam. So in summary, the siding and mainline track, we had a total of 23 weeks of FFU installation, all in non-disruptive possessions. It was completed by re-railing and fitting the check rail. So in total, we have 200 FFU sleepers and 12 FFU way beams. And here we see completion, and the left-hand photo is the view looking from span 5, looking in span 4, contrasting the way beam with the sleepers. The check rails fitted in 2021 to complete the works. And this is before and after photos of the track work. So in conclusion, with the deferral of the 2013 track renewal, what seemed a setback at the time was turned into a positive outcome through the focused rethinking the track design for sustainability and by the use of new composite materials. The interventions to repair and upgrade that we've made all will sustain the bridge for many more years of service. We've increased levels of safety and reliability as we've eliminated timber rot and risk of track twist. We have extended the time to track renewal and eliminated the timber steel interface, which will reduce corrosion to the bridge structure. We've introduced low maintenance composite materials that can be recycled at the end of life. And also for our customers, we've delivered a benefit of speed improvement across the bridge. So just to acknowledge, maybe that's with all projects this nature, there's a team behind it. I'm not going to mention people individually, but just acknowledge there's a team and thank everyone involved with the delivery of the upgrade of the project. And that concludes my presentation. Happy.